Voice is clear and audible. Welcome again to this session of European Chatbot Conference. With me, Duygu, your senior NLP developer from DeepGram. We are a professional speech and language company from San Francisco, California, and we are very excited to meet you today. In this session, we will present the topic transfer learning for creating highly accurate new language models. This talk is divided into 4 sections. First, we start with a quick history of transfer learning. We will see what is transfer learning, what transfer learning introduces to statistical modeling, and then how transfer learning works for text modeling. In the second part, we will make an overview of speech recognition modeling at DeepGram. First, we will see our in-house model types, then we will go over the stages of the training. Final point of this section is model packaging, which is a crucial part of this talk. The third section includes how we use transfer learning for speech recognition at DeepGram. We focus on 2 headlines here: transfer learning for improving a model for a specific language, and transfer learning for creating a model from scratch for a new language. Here, we will focus on tools and techniques we use at DeepGram. Final section introduces a case study. We will see a solid example of creating a model for Portuguese language by transferring the knowledge that is contained in the Spanish model. Here, we talk about the intuition behind picking the Spanish as a base for Portuguese, similarities between these 2 languages, including acoustic similarities and vocabulary overlap. We present the results, then we go over the other possible language pairs where transfer learning is applicable. Transfer learning is one of the hottest topics of NLP in recent years, and indeed in our lives. Starting with the word vectors, transfer learning reached the point of giant language models called transformers. Transfer learning started its journey with word vectors, which provide static vectors for each word in the corpus. Then contextual word vectors came with ELMO. Transformers came with generating contextual word vectors and a sentence vector, which is even better. At the very end, we are all looking for good representations for our corpus words, which happens to be vectors. Both pre-trained word vectors and transformers are trained on giant corpora, hence knows a lot about the target language's syntax and semantics. We feed pre-trained vectors to our downstream models, and the vectors bring what they know about the language, semantics of the words, and many surprising features to our models. This slide includes 2 pieces of code where almost every machine learner who is watching can recognize. On the left-hand side, we see how to import pre-trained word vectors of fast text into a Keras code to be used in a downstream NLP task. Here, one downloads the pre-trained vectors from fast text web page, place it on the local file system somewhere, load them, and use this vector in an embedding layer, which is a lookup table basically. This code segment evolved to the code segment on the right. Here, transformer took the place of word embeddings. Also, the vector size and the other vocabulary computations went under the hood of transformer. First 3 lines configures the transformer, next 3 lines places transformer as a Keras layer, then next 2 lines makes the classification. Code is much shorter and compact, definitely less computations about vectors. Definitely the code and the ways are different, but still at the end, both methods provides vectors. In order to understand how transfer learning blends with speech recognition, still we have a step in between how speech recognition models are built at DeepGram. We have 2 types of models at DeepGram. One type is called a phoneme model, and the second one is called a word model. Phoneme models like one on the left, generate phonemes from the speech, where a phoneme is the unit of language's sound system and also a way to systematically represent the sounds on the paper. So the transcription on the left-hand side shows the acoustic representation of input words, whereas a word model transcribes the speech into words, just like the example output on the right. Every language has a different phonetic system as well as a different vocabulary of words. Hence, each language needs their own model to be trained. Coming to the model training phase, we make the training in several phases. The training data consists of speech files and their corresponding transcriptions. We feed them to a aligner model to generate aligned data, which is the words in the transcript aligned to the time frames they occur in the speech file and the speech file itself. Basically, we generate a more sophisticated intermediate training data form so that during the real training, we can extract richer features to learn. We use phoneme models as aligner models, so aligning phase focuses on the phonetics of the language. After that, we train the word model on the aligned data. There are more data preparation steps in between the aligning and the training, including segmenting speech, but I didn't include them in the diagram, not to drown in the details. Overall, speech recognition is not an easy task. As you see, it needs several phases. Also, training is a cycle. After aligning the training data, we have a better version of the aligned data, so we can train better version of the aligned data, so we can train a better version of the phoneme model. So our training cycle is align, train, and so on. It's a cycle. After the model is trained, we need to package the model for testing and production. A model package includes all the information so that this model can be correctly deployed. A package includes the model info file, where model metadata is written, such as the speech sampling rate, the language, and so on. We also include vocabulary strings in the text format with their weights, such as the example on the right. And again, we also include the model weights, which are weights of the neural networks we used during the training. Now comes the part how transfer learning fits into speech recognition exactly. In DeepGram, transfer learning is highly valued. For a specific language, when we want to train any version of a specific model, we don't want to start from the scratch. Instead, we want to carry the knowledge of the previous model. With our packaging and training system, it's indeed very easy. Basically, we copy over the package of the previous version into the current training directory where we do the training and rename it to initial.weights.tar. There is a line in the training configuration, as you see on the right side, which means use the final weights in the initial weights.tar, the tar file, as the initial weights of the new neural network. That's it. We transferred the knowledge of the previous version just in 2 steps without much effort indeed. And when we want to train a model from scratch for a brand new language, we want to transfer some knowledge from a similar language's model when possible. First of all, we need a phoneme model, which doesn't exist yet. At this point, for the initial aligning task, we use the similar language's phoneme model. After aligning, in the training phase, we don't have to start with the code weights. Instead, we can transfer the vectors of the common vocabulary words. We also allow a reasonable edit distance because words usually do not occur exactly in the same characters, such as the example liberté and libertin. For transferring the weights, our training suite has a dedicated command. Basically, you run this command, pass the name of the model that you want to transfer the weights from. This command compares the vocabularies, finds similar looking words with a reasonable edit distance, and forms the initial weights.tar. So this command actually works in several steps, but still it's only one command. So transfer learning is quite effortless in our training suite. As seen, we don't like to start with a blank model in any case. We want to bring as much as information from already trained models in any case. So, does it really work? Let's see it with a real example. Being both Romanic and highly related languages, our happy pair of today is Portuguese and Spanish. First of all, let's see the acoustic similarity. You see the phonetic alphabet for both languages side by side. Consonants are actually very similar. Vowels are quite similar as well, only Portuguese has more vowels. So Portuguese phoneme model can be built upon the Spanish model easily by adding some extra vowels. Let's see the acoustic similarity on action. Left-hand side includes the spectrogram for the word cinco in Spanish, whereas the right-hand side shows the spectrogram of the same word pronounced in Portuguese. Pronunciations are different, yet spectrograms look quite similar. If we look at how the energy is distributed on the bands, vertical bands called as formants, we can see that vowels are quite similar too. This part gives us the clue that Spanish phoneme model indeed can align Portuguese data successfully. Coming to the second part of the transfer learning, we focus on the vocabulary. Left-hand side shows Spanish words, right-hand side shows Portuguese counterparts. As we see, vocabulary words are quite similar. Some words are even the same. And some are with a really small edit distance, maybe one character. So transferring word weights should be successful too. Now the results. For a comparison, I exhibited the first version of the German phoneme model versus the Portuguese phoneme model. First version of German phoneme model's training curve is exhibited on the left-hand side, and the right-hand side exhibits the first Portuguese model. We use English phoneme model as the first aligner of the German data. Hence, if we look at the first images on the both sides, Portuguese loss went down in a more steep way. The second figures show the word error rates of each phoneme model. Portuguese phoneme model started around 0.9, were around 1% less than the English phoneme. At the very end, Portuguese phoneme model converged around 35%, where English phoneme model went down to 40%, where. This is quite expected because English and German are cousins, whereas Spanish and Portuguese are siblings. Closer the language pairs, the better they produce results. Finally, can we make of the transfer learning useful for other language pairs? That's for sure. Germanic languages form a group, Romanic languages form another group, and definitely there are more groups to be trained. This concludes our presentation, and I am quite happy to get the questions. Again, many thanks for your participation, and we wish to meet in the oncoming events.